Let's take a look at the inverse trigonometric functions. A statement like sine theta equals 1/2, it involves a trig function, sine, and that function relates an angle, theta, represents an angle with a ratio. And the definition of the trig functions, we develop these by looking at ratios of side lengths of right triangles. So that ratio, it corresponds in some way to a right triangle. And so all of the trig functions, they make this connection. They relate an angle to a ratio. The inverse trig functions go the other way. So for an inverse trig function, what I'd like to do is start with a ratio and turn it into an angle. So, for example, the notation for this, sine inverse, would be written with sine, S-I-N, and then a little -1 as a superscript next to that. And so, for example, sine inverse of 1/2 is going to correspond to an angle that has 1/2 as its sine ratio. And so this is going to take the ratio and turn it into the angle. But there's a problem, there's kind of a complication here. The trigonometric functions are ultimately defined using the unit circle and angles in standard position. And so the ratio of 1/2, it corresponds to a point on the unit circle that point can be achieved, can be related to a whole bunch of different angles. So this point would give us a sine ratio of 1/2 on the unit circle, and it corresponds to a 30-degree angle, but also to a 390-degree angle if I go a full rotation beyond 30 degrees. If we go in the negative direction, it could be negative 330 degrees. And what's more, we could even get a sine ratio of 1/2 by looking over in quadrant 2 at 150 degrees. So all of these angles have a sine ratio of 1/2. A function, however, needs to have a well-defined output. And so if I take a ratio as an input, I need to have exactly one angle come out as the output. And so to define inverse trigonometric functions, we need to choose some sort of restricted set of angles. We'd like our choice to be as simple as possible, so we'd like it to be sort of numbers that are small, maybe close to 0, and preferably positive. And so we'll take a look at the sine and other trigonometric functions and see how we choose the restricted set of angles in order to create an inverse trig function. So if we think about the sine function graphically on the xy coordinate plane, the x values of the sine function, they represent angles, and the y values of the sine function, they represent ratios. The inverse trigonometric function is essentially, it switches the relationship. It turns the ratios into the x values and the angles into the y values. And so in order for that to be a function, we need to have just a single set of angles that correspond to the complete set of ratios. Well, the ratios for sine, they go between +1 and -1. So we want to capture all those possible ratios, but to do it with kind of the simplest set of x values, well, this peak is the closest, positive peak. We could choose this as our lowest point and go between pi over 2 and 3 pi over 2, but that's not the simplest choice. In a sense, it's kind of simpler to go between the peak at pi over 2 and the valley at negative pi over 2. And so that's the choice that we make. That's the set of angles from negative pi over 2 to pi over 2, or from negative 90 degrees to positive 90 degrees. That's the set of angles that gives us the full set of possible ratios. And so when we say something, when we make a statement like sine inverse of 1/2 equals some angle, that angle has to be between negative 90 degrees and 90 degrees. Or in radians, it has to be between negative pi over 2 and pi over 2. So this statement, in order for inverse sine to be a function, there needs to be an exact angle, one single angle that corresponds to that statement, and that angle is the angle in this range that corresponds to a sine ratio of 1/2. And so it would be 30 degrees or pi over 6. On the unit circle, this diagram corresponds to the angles from the positive y-axis through to the right here through to the negative y-axis, from pi over 2 or 90 degrees to negative pi over 2. So this would be the set of angles that are possible outputs for the inverse sine function. So let's compare this to the cosine function. The cosine function starts at 1, cosine of 0 is positive 1, and going in a positive direction when we get up to pi, cosine of pi is negative 1. Because cosine corresponds to the x coordinates on the unit circle. And so at 0 we start at a cosine value of 1. And so the simplest choice that we can make for cosine is to take the set of positive angles, from 0 to pi. This gives us a full range of cosine values from positive 1 down to negative 1. And so the inverse cosine function, if we take inverse cosine of, let's say, negative 1/2, the angle that corresponds to that is going to be the angle that corresponds to, on this diagram, that corresponds to a y value of negative 1/2. And so that angle turns out to be 120 degrees, or in radians, 2 pi over 3. Thinking about this on the unit circle, it corresponds to the unit circle in quadrants 1 and 2, because for cosine, that takes us from positive 1 at 0 all the way to negative 1 at pi. And so the set of angles from 0 to pi gives me a full set of ratios for cosine. Well, it turns out that the other trigonometric functions, they follow sort of a similar pattern. For cosine, for cotangent, and for secant, the basic sort of range of angles is going to be from 0 to pi. That's the way that we define, I should say, inverse cosine, inverse cotangent, and inverse secant. For sine, cosecant, and tangent, the basic set of angles that we're going to use go from negative pi over 2 to pi over 2. And so that's how we define inverse sine, inverse cosecant, and inverse tangent. So thinking about those angles, let me end with the following question. What would be sine inverse of negative square root of 2 over 2? So what angle, given these parameters, in particular given the fact that the angle has to be between negative pi over 2 and pi over 2, or in degrees, negative 90 degrees and 90 degrees, what would be the angle that corresponds to the ratio negative square root of 2 over 2? In a similar way, for cotangent, what would be the angle that corresponds to a cotangent ratio of 1 over the square root of 3? I encourage you to take a few minutes and think about those questions. I hope you enjoyed the video. Thanks for watching.